All right. Question 9, the pH of Coca-Cola is 3.8. What is the hydronium ion concentration? All right, we know hydronium ion equals 10 to the negative pH. So my hydronium ion concentration equals 10 to the negative 3.80. All right, 10, oops, wrong button. 10 to the negative 3.8. And I get a hydronium concentration of like 1.6 times 10 to the minus 4. Again, we went from pH, so pH, only these two numbers count towards significant figures, which means in my concentration, I just need to have two decimal places. So it looks like choice A is the correct answer there. Two decimal places in pH means two significant figures for my concentration. It's only when you're going from concentration to pH or pH to concentration that the number will change. It'll look like you're gaining or losing a significant figure. If it's concentration to concentration or pH to pOH, right, it would stay the same. All right, question 10. Oh, it looks like I don't have question 10. I don't have question 11. Question 13 looks like it's up next. All right, question 13. A buffer contains 1 molar propionic acid, 1 molar sodium propionate, which I identify in the question as the conjugate base. So that tells us we've got a buffer question, right? Not only did it say a buffer, but we've got an acid, its conjugate base. To that buffer solution, I add HCl. So let's draw this out. Got my buffer. All right, I've got my weak acid, my conjugate base, 1 molar of each of those. And then to that, I add 0.115 of a strong acid. All right, my strong acid reacts with the conjugate base, right? Conjugate base plus acid is going to give me more of my weak acid. So it should make sense. If you're adding an acid, I should expect to see that concentration go up at the expense of the concentration of my conjugate base. That concentration should go down. So we want to add to our acid side. So I'm going to add 0.115, so 1.115, and I'm going to subtract here 0.115, so what's that, 0.885, I think. All right, so after the acid reacts, it is all gone. Both concentrations need to change. And after the acid reacts, I'm left with 1.115 of my acid and 0.885 of its conjugate base. Now I can use the Henderson-Hasselbalch equation to find the pH of this solution, right? pH equals pKa plus the log of my base over my acid. So pH equals, remember, pKa is the negative log of my Ka value. So negative log 1.3 times 10 to the minus 5 plus the log of my base concentration, 0.885 over my acid concentration, 1.115. So pH equals negative log 1.3 times 10 to the minus 5 plus the log of 0.885 divided by 1.115. And I get a pH of about 4.79 for this buffer question. Right, we're adding a strong acid to it. We should expect to see the concentration of the weak acid increase. We should expect to see the pH go down. All right, it looks like question 15 is up next. We'll do 15, 16, 17, and 19. Oh, okay, yeah, question 15. We did this on Friday. A couple of steps here for question 15. We have to find concentration, right? Our pH is tied to our concentration, so that's step one. Got 120 milligrams. We know concentration molarity is moles per liter. So I have to turn mass into moles and then concentration. So 120 milligrams, there's 1,000 milligrams in 1 gram. So I've got 0.12 grams. I gave you the molar mass for a reason, right? There's a hint. I need to use that, 1.7612 grams for 1 mole. So 0.12 divided by 176.12. And I get like 6.8 times 10 to the minus 4 moles. We have that in 0.25 liters, right? Molarity is moles per liter. So I want to turn this into molarity now. So 6.8 times 10 to the minus 4 moles in 0.25 liters. I get 2.73 times 10 to the minus 4, minus 3 actually. And that's where a few people I was working with last week, they wanted to take the negative log of that and call that pH. We can't. We can't because this is a weak acid. We know this is a weak acid because I give you Ka values for it. Yes, there are 2 Ka values, but we talked about polyprotic acids, acids that can donate more than 1 proton in class. And when we talked about them, we said the second Ka value, especially in this case, the second Ka value is so small, it can be ignored. Correct. The first acid dissociation constant is the major one because that's the easiest proton to lose. The second proton is always going to be harder. So this is my concentration of my vitamin C, which is my concentration of my weak acid, basically. So we have a Ka calculation, right? Ka, hydronium, conjugate base all over my weak acid. So 7.9 times 10 to the minus 5 equals, right? I don't know hydronium. I don't know conjugate base. My concentration of the acid, 2.73 times 10 to the minus 3. So we're going to multiply that across, get x squared times 7.9 times 10 to the minus 5, 2.15. Square root on both sides, and x equals 4.64 times 10 to the minus 4. Now we have found our hydronium concentration because we finally found X. Now I can find the pH. All right, so 4 steps here. This is a longer problem, but it's the practice exam. I think it's good to work through some harder problems on the practice exam. pH is the negative log of 4.64 times 10 to the minus 4. pH equals, all right, I get 3.33 as my pH. So choice A there for question 15. Looks like question 16 is up next. Yeah, question 16 is just kind of a conceptual problem. Like, how does a buffer work? Why does a buffer work the way that it does? Right. And so if I have this 1 liter buffer and I've got my weak acid, HF, and its conjugate base, fluoride, in solution. And to that, I add a strong base. I add sodium hydroxide. What is going to happen to this buffer? Well, my weak acid, HF, is going to react with a strong base, right? Acid-base reactions. And the product of that reaction is water and more fluoride. So what happens is HF concentration goes down, fluoride concentration goes up. So, and our pH will go up as well because we're going to have more conjugate base, right? We added a base to that, so we should see an increase in pH, which should make sense. We're adding a base. Bases have a higher pH. So concentration of HF increases. Nope, we know it's the opposite, so we can cancel out that. We know all the hydroxides react, so we can cancel out D as well. The concentration of HF decreases, yeah, because the hydroxide reacts with it, and as a result, the pH increases. So choice C for question 16. All right, we'll do 17, 19, and then I'll take a break there. I mean, it's fair game, right? It's how does a buffer work and why does it work that way? So it's just a conceptual question. Do we understand why a buffer works the way it does? If you can do the calculation, right, we should be able to understand that, okay, both of those concentrations are going to change. In this case, the acid goes down, the conjugate base goes up, and because I'm adding a base, the pH would go up as well. So I would say, I can't tell you exactly, but I would say question like 16 is fair on the exam. Yeah, we're working towards question 24. We'll get there. All right, question 17 is also a harder question because we are mixing two things together, so it's a little bit more involved. We're mixing this much of our acid and this much of our conjugate base. So we need to do a little bit of a calculation first. All right, our first calculation, we want to find when we mix those two solutions together to make our buffer, the concentration changes. So we want to use M1V1 equals M2V2. So we'll do that for hydrogen cyanide. All right, we get my initial concentration is 0.5. My initial volume is 375. My new concentration at my final volume, which is 1,000 milliliters. Do the same thing for the sodium cyanide. Right, 0.5, 625. Our new concentration at 1,000 milliliters. The 1,000 milliliters comes from, right, when I make this buffer, I add 375 of the one solution with 625 of the other solution. And that's how my final volume ends up being 1,000 milliliters. So multiply, divide. So let's see, 0.5 times 375, divide that by 1,000. I get a concentration of 0.1875 for my acid, and then 0.5 times 625, I get 0.3125 for the conjugate base. Now I can do the Henderson-Hasselbalch equation and find the pH of this solution, right? pH equals pKa plus the log of my base concentration over my acid concentration, right? So pH equals pKa, negative log of 6.2 times 10 to the minus 10 plus the log of my base concentration, 0.3125 over my acid concentration, 0.1875. So negative log 6.2 times 10 to the minus 10 plus the log of 0.3125 divided by 0.1875. And I get a pH of like 9.43. Again, the hardest part of this question was just finding the concentrations. We mixed the two solutions together. We had to go through the M1V1 equals M2V2 to figure out our new concentration after we'd mixed the two solutions together. So for this question, question 17, you probably won't have both parts together. It would probably be more just like the second half of this. I give you the concentrations and ask the pH. I don't ask you to find the concentrations. So I think part one, right, takes a little bit of time right here. So you may have to find the concentration in another question, but in terms of a buffer question, it would be more of just the second half. What is the pH when I have this concentration of an acid, this concentration of my conjugate base? All right, so that should have been C, I think. All right, question 19. We kind of talked about this on Tuesday. All right, calcium oxalate is a common form of kidney stones. Oxalate, and I tell you, oxalate is, here's the important part, all right, oxalate is the conjugate base of oxalic acid. So it is a conjugate base, right, which means it's going to behave like a base. So if I have this equilibrium, right, calcium oxalate ionizes to give me calcium oxalate. If oxalate behaves like a base, that tells me that under acidic conditions, I should be able to protonate that and remove that from this equilibrium. So Le Chatelier's principle says, right, if we remove something from a system at equilibrium, the equilibrium will move in a direction to replace what was lost. So if I'm able to make this more acidic, it should be more soluble, because under acidic conditions, I'm going to protonate this conjugate base that removes it from this equilibrium that allows more calcium oxalate to go into solution. So we would want to be on the more acidic side of that pH range. So certainly comparing 7 to 8, like 7 would be better, but pH 6.5 would be even better. It would be even more soluble under those conditions. So we'll take a break there, and then I'll get together and do question 20, 21, 22, 23, 24, and 25.